Welcome back to this lecture on set operations. In this third segment, we are going to go through a list of set identities or set laws, that is, properties of the operations of union, intersection, and complementation. For the vast majority of these identities, maybe all of them, you will either know them already because we discussed them in an earlier segment of this lecture, or they will be intuitive and easy to remember, or they will be strongly analogous to laws that we study back in logic. In particular, you should watch out for the similarities between the set operations of union and intersection and the logical connectives disjunction and conjunction. Now let's get started with our first set of identities or laws, and the first one is the identity law. There's two of them, and they state that for any set S, the union of set and the empty set is the set S itself, and similarly, the intersection of any set S with the universe is the set S. The second set of identities are called domination identities. The first one states that for any set S, the union of S with the universe is the universe, and the intersection of S with the empty set is the empty set. The next two identities are called idempotent identities, and they state that for any set S, the union of S with itself gives you back S, and similarly for the intersection. The next identity is called complementation, and it states that the complement of S is nothing but S for any set S. The next two identities are called commutativity laws. For any set S and T, the union of S and T is the same as the union of T and S. And similarly for intersection. In other words, the order of the operands of union and intersection does not matter. We also have De Morgan's identities for sets. Namely, the first one says that the complement of S union T for any sets S and T is the intersection of the complement of S and the complement of T. And similarly, when swapping the union and intersection operations. The complement identities state that the union of S and its complement is equal to the whole universe, and the intersection of S and its complement is always the empty set for any set S. The absorption identities are as follows. If you take S and union it with the intersection of S and any set T, you get the set S back for any set S. And similarly, when you swap the operations of intersection and union. The next two identities are called associativity identities, and they state that for union as well as for intersection, the order in which the operations are performed from right to left or from left to right does not matter. You always get the same set back. Let's start a second column for the last pair of set identities called distributivity. The first such identity states that for any sets R, S, and T, the intersection of R and S union T is the same set as the union of R intersect S and R intersect T. Now, of course, we haven't proved any of these identities so far, and we're not going to prove this one either. However, we're going to illustrate this particular one with Venn diagrams. Again, this is not a proof, just an illustration of the identity, and the reason it's not a proof is because it does not cover all possibilities. there's only one way I'm going to draw the sets R, S, and T in a Venn diagram, and this way does not cover all the possible ways that those sets could relate to each other. So this is just an illustration, but hopefully it will convince you that this identity holds on an intuitive level. So first we draw the universe containing the set R, then I'm drawing a second set S, and a third set T. Notice all the sets intersect pairwise with each other. That's not always the case, but that's the most general situation. And now I'm going to focus on the left-hand side of this identity, and I'm going to color the elements that belong to this set. So first, I'm going to consider S union T, which is represented by all the elements in blue in the Venn diagram. Then I'm going to take the intersection of this blue set with the set R to get the set on the left-hand side of the equal sign, and these are all the elements in red. Now, I'm going to turn my attention to the right-hand side of the identity, and I'm going to build another Venn diagram that starts out the same, and then I'm going to color the elements according to the set operation. So first, I'm going to focus on the intersection of R and S. I'm going to color these elements in green. Then I'm going to proceed to the second intersection, namely R and T, which I'm going to color in purple. Here are those elements. And finally, I'm going to take the union of those two sets, the green set and the purple set, so that I can represent the set corresponding to the right-hand side of this equation. And what you notice in this case is that the two sets in the two Venn diagrams are indeed identical. Again, this is just an intuition for how this identity works, not a proof. Let me conclude this segment by giving you a second distributivity law that's obtained simply by switching the intersection and union operations. And here it is. I will let you draw a Venn diagram for this one to at least convince you that it works in some cases, and we'll stop this segment on this identity.